Hello everyone, welcome back to the mechanical vibrations tutorial. Today we are going to study the vibration of systems under non-periodic force. So let's begin. So as you may remember, the systems under a force could be studied when the force is harmonic or periodic. We have shown different methods of analyzing systems under such forces. So let's draw a simple 1 degree of freedom system with a spring, mass and damper. And you remember the equation of motion was mx double dot plus cx dot plus kx, and if we have a force Ft applied to the system, this is equal to Ft. And then for Ft we had the cases that the force was periodic, right? So for the periodic case we had also two cases. The case that the force is harmonic, which means that the function is a cos or sine function, like sine omega t or cos omega t, right? And omega is the frequency of excitation. We also had the case that the force is periodic, but it is not harmonic, and we call it non-harmonic. And we showed that before, right? For example, we had the cases that the force is applied with triangular but repetitive shapes under a period of time, right? Now we want to study another case that the force Ft is not periodic, so we call it non-periodic, right? Okay, so what does that mean? It means that the force does not follow any sort of repetitive behavior, or there is no sort of frequency or period associated with the force. For example, imagine Ft has, say for example, a sort of this shape or another shape. For example, we have a force like this, or we have a constant force, and so on. There are many different examples existing in the real world applications that the force applied to the system is not periodic, and we need to find the response for such systems. Okay, so that's very interesting. So let's see how we can study such systems. To start with studying such systems, first we need to understand the case that the system is under an impulse. So an impulse is an instantaneous force that is applied to the system. Normally you can show the impulse at the beginning of like a time zone. For example, if it's t and this is Ft, we can suppose that the force as an impulse is applied at a very short time, and the amplitude is, for example, f, like capital F, right? It seems that the force is only applied at the very beginning, right? It's kind of mimicking this case. There is no time span for the force, right? So for these cases, the impulse can be behaved as an initial condition. Basically, an impulse is sort of related to the impact and velocity, if you remember from the dynamics. So the impulse can be interpreted as an initial condition, say for example x dot naught at F over m, where m is basically the mass of the system. And like I said, it goes back to the impulse momentum relations and how we can relate the force to the initial velocity of the system, right? I don't want to go to the dynamics, but you can remember or you can review your dynamic courses to understand that. For such systems, we can simply say that the system has an initial condition which is resulted from the impulse. So the response of the system, we can simply find it based on what we had before, when there is only an initial condition and there is no force. In that case, xt, the time response of the system for 1 degree of freedom case, is equal to f e minus zeta omega n t divided by m omega d sine omega d t, right? Very simple. We can find it from before. And normally this part of the response, we can also call it as gt, and I'll tell you why we use gt here. So now imagine the case that the impulse is applied to the system not necessarily at the beginning of the time span. So this is Ft, but the force is applied, say for example, after a period like tau. So there is an impulse in the system like in here, right? And the amplitude of this impulse is F. For this case, we can also use the above equation to find the response of the system. So in this case, xt is equal to f gt minus tau. So in fact, we just need to use the above equation, and instead of t, we have to use t minus tau. Why? Because the response, or basically the impulse, is applied to the system, not necessarily at the beginning of the motion. So for example, for this case, if the response of the system, like say for example here, is something like this, for this one, the response is started from here and then damped because of the damping. And for sure, if there is no damping in the system, we get rid of the E minus zeta omega n t term in our equation, right? I know you understand that because zeta is related to the damping, right? So why we started with the impulse and why we basically discussed the case that we started from the beginning and the case that we have the impulse at the period of tau. I'll tell you why. We want to study the case that the force is not periodic. So imagine for the force of, say for example, this is Ft, we have any arbitrary sort of equation for Ft which is not periodic, say for example something like that, right? We never know the equation, but for sure it's not a periodic function. So how can we deal with this case? We can simply divide this force into infinite impulses. So one impulse at the beginning, the other impulse at a short time, the other one, and the next one, and for example somewhere here, if this is tau, somewhere here we have another impulse. So the whole force could be treated as the summation of multiple impulses, and we already know the response for one impulse. So we can put them together or put it in the form of a summation by integration, which is also known as the convolution integral, to basically sum up the responses because of this type of force. So basically in that case, xt can be found as the convolution integral, which is the integral from 0 to t. So as you see, the lower bound 0, upper bound is t time, but here it's for the integration purpose we take t as a constant. F tau, so f is the function and tau is the variable of the integral, g t minus tau d tau. So here is the function, or basically the integral that we can use to find the response of the system. So then the response would be easier to deal with, and xt would be 1 minus m omega d. In fact, I'm substituting g t minus tau into the equation or to the integral, 0 to t f tau e minus zeta omega n t minus tau. If you recall the function for g, we had e minus omega n t, which is now switched to t minus tau, right? Sine, this is sine omega d t minus tau d tau. So for these types of systems, it is pretty much integration to find the response, no other trick. If we calculate the integral properly, we can find the time response of the system. So here in this integral, f tau is coming from the function related to the force, and this part is coming from, and especially this one, so these two parts coming from g t minus tau, right? So as you see, it is a general formula that can be applied to the case that the force is non-periodic. For the case that there is no damping in the system, it is even simpler. So imagine that we have a spring mass system, so k and this ft is any non-periodic function. So this is ft, for example, something like that, right? Or I don't know, it could be an increasing force, decreasing force, anything, right? For this case, because there is no damping, we only need to calculate the integral when there is no damping component. So it is even easier. So there is no omega d now. We deal with omega n. Why? Because zeta is equal to 0, because c is equal to 0, right? So for this case, xt, the response of the system is 1 over m omega n, integral of 0 to t f tau. So there is no e here, sine omega n, or let me raise this bracket. So we have basically omega n t minus tau d tau. So as you see, it's even easier because there is no e or exponential term in the integral, which makes the integration faster and simpler. Remember that here the variable for integral is tau. So basically there is no t, or we can treat t as the constant and find the integral. So remember, this is f tau. So any function for f, we need to switch t to tau to do the integral, right? So probably you need to review your integration or basically your math knowledge to solve this sort of integration. I'm gonna give you one example. There are some special cases for these types of excitation that could be a bit tricky, especially when the force stops after a period, for example like this, or for example like this. Then we have to define a piecewise function and deal with the integral differently. I'm gonna show this example or these types of systems in the next tutorial. So let's begin with our example and see how we can use this convolution integral. So in this example, we want to find the time response of the following system when the force is represented as an exponential function and it is a decaying force, right? As you can see, the force function is not a harmonic or a periodic force. So this is a pretty simple case that the system has only a spring and mass. So we can write down the equation of motion as mx double dot plus kx is equal to ft, and if we plug in the numbers, we can simply have 11 x double dot plus 112.5 x equals to 5 e minus t. So as you can see here, the force is a decaying exponential force, which means that if we draw it approximately, it starts at 5 newtons. So this is ft, and because it is minus t, or the power for the exponential is -1, it is decaying and goes to 0 as t increases. So we have multiple impulses and we can treat the system based on the convolution integral. And because there is no damping, it's even simpler. So xt is going to be equal to 1 minus over m omega n, the integral from 0 to t f tau, and then we have only sine omega n t minus tau d tau. So this is ft. So when we do the integral, we have to convert it to f tau. And what is omega n here? The omega n is very simple. Omega n is equal to the square root of k over m, and we know k and m, which gives us 3.198 radian per second, right? So let's do the integral and see the tricks that we can use to find the integral, okay? Now we want to find the response of the system, and basically I should notify you that in many examples you have to first simplify the example and find the equation of motion, equivalent masses, equivalent stiffness, and equivalent damping, then apply this convolution method. So don't go to this convolution integral and this procedure directly. Sometimes the system has more components and they are related to each other, So you have to simplify it and then apply this method to the system. The reason that here we have a very basic example is I think you have already learned how to simplify the system and how to find the components of like a equivalent component of the system. So basically what we have here, xt is equal to 1 over m omega n 0 to t. Ft is 5 e minus tau. Why tau? Because the variable of the integral is tau here. Sine omega n t minus tau d tau, right? And we can basically take this 5 out and calculate for m and omega, because we know m and omega n. So xt would be equal to 0.14 0 to t e minus tau sine omega n t minus tau d tau. So remember, this 0.14 is basically 5. This is actually 5 over 11 times 3.198, just in case you don't know how we calculate that, right? So in order to simplify this integral, again, you need to review your calculus knowledge on integration, or we have very great videos that you can basically find to basically know how to deal with different integrals or derivatives. So as you can see in here, we need to simplify this integral. So what I want to do, I want to add some terms into the integral that doesn't affect the integration. So in here basically I want to add something. So I want to multiply the whole integral into et times e minus t, right? Because et times e minus t is equal to 1, so doesn't change anything. We can put it in there. So basically x t could be equal to 0.14 0 to t e minus t, doesn't matter, we can flip them, times et times e minus tau sine omega n t minus tau d tau, right? I hope you understand what I did. So let me just make it a little bit clear. So if I go back, so I rewrite it just for better representation. So we have sine omega n t minus tau d tau, right? So we basically multiply the integral with these two components, which doesn't change anything. Why we did that? Because we can simply combine these two to each other, right? So let me just draw a line here so that you don't get confused with that, right? So what we did, we basically added these two components to further simplify the integration. So these two can get to each other. So xt would be 0.14 0 to t e minus t times e t minus tau sine omega n t minus tau d tau. See, because there is the multiplication of two exponential terms, we can add the powers together, which in fact give us t minus tau, right? So why we did this, I think you can understand it, because we want to create this t minus tau into both functions. And as you see, this is a constant because the variable is tau, so we can put it out, right? Like I said, it is more of integration now. So if we do so, and I further simplify the integration, we get xt equal to 0.14 e minus t 0 to t e t minus tau sine omega n t minus tau d tau. Now I want to define a new variable, so I put t minus tau equal to u, which means that basically d tau is equal to minus du, right? Because t is a constant when we take the derivative here. And now we can basically plug in everything into the equation. So let's forget about the upper bound and lower bound for now, and just keep it as xt equal to the integral minus, and this minus is from here, 0.14 e minus t integral of e u sine omega n u du, right? So that's why we define u, because we want to even make it simpler. So this is what we end up now. So like I said, let's forget about the upper bound and lower bound. In the future, we return or we switch back u to tau, and then we can use the upper bound and lower bound, right? So this is a famous integral. Basically, this is a famous integral, and you can find the response, or basically the solution for this integral. Or let me write down again. If you use some handbooks, or if you find on internet, the integral of e a u, where a is a constant, sine b u du is equal to e a u divided by a squared plus b squared times a sine bu minus b cos bu, right? So this is a formula I found from some handbooks, and I don't need to calculate this integral. Anyway, you can find this integral by some integration by parts and repeating that. For this case, a is equal to 1 and b is equal to omega n, right? For our case. So keep that in mind, right? So now we want to apply these all definitions and basically further simplify the integral. So what I'm gonna do now here is to use this equation here and basically replace a by 1, b by omega n, and then I switch u to t minus tau, because we want to find everything based on that, right? So that's just to say what I'm going to do now. So if I do so, and if I basically do all the process, xt would be equal to minus 14 or minus 0.14 e minus t times, we can use the formula I said before, e t minus tau. So this is instead of u, divided by 1 plus omega n squared. This is actually, you remember, a squared plus b squared times sine sine omega n t minus tau, right? Which was a times sine bu, if you remember, minus omega n cos omega n t minus tau, and we close the big bracket here, or let me do it this way, and that's it. Now we can apply the upper bound and lower bound equation or boundaries of integral, which is 0 and t. So imagine for this basically function, wherever we have tau, we need to plug in t and 0, right? You know how to calculate the integral, definite integral, right? So you don't have to be worried about that. It's pretty simple. So after we do this, we can simply find the final response of the system, and after some calculation and plug in omega n. Just for the sake of simplicity, I want to show you the final response of the system, which is equal to 0.0405 e minus t, and for sure you can double check my calculation, plus 0.0127 sine 3.198 t, which is, you know, our frequency, and 0.0405 cos 3.198 t, right? So this is the final response of the system, and like I said, you can double check my calculation. So as you noticed, we applied the convolution integral and we found the response of the system when the force is like a decaying exponential function and it is not a periodic force. In the future tutorial, I'm going to show you another case which is also very important for these types of systems. So I hope you enjoyed this video and stay tuned for the next videos.